Hello everyone, and in today's video, I want to go over on a much deeper technical level on what embeddings and vectors are within the context of large language models and how you can leverage embeddings and vectors to build your own LLM applications. So a big part of how LLMs work involves this idea of embeddings. And from my experience, I realized that while conceptually we might understand what embeddings are and the purpose that they serve, oftentimes we lack the technical understanding and the realities behind them. And today I want to pull back the curtain and dive into not just the what, but also look into the how and why of what embeddings are. So if you find this information helpful or you want to learn more about AI, ML, and how to build applications on the cloud, then you might consider liking, subscribing, and commenting. It really helps with the algorithm as well as push this information to a wider audience. So what do we mean when we are referring to vectors? So when we say vectors, we are referring to just a way where we take various forms of data, it could be text, image, audio, and we convert it into a uniform format known as vectors, which are essentially just an array of numbers. And each number here in this vector is basically corresponding to a particular feature about that input data. See, each unique input is converted into a vector, and this is done through an embeddings model. So the embedding model is essentially a type of neural network that is trained to capture the essence of the data. So in the example that, for example, you're working with text data and you're creating a search engine, you might be concerned with search results that are very similar in meaning with the words that are being prompted by the user. And choosing the appropriate embeddings model is able to give you and yield you better results because you're able to pull words that maybe are closer in meaning together through this embeddings model. So the reason why I mention this is because it leads me to my next point, which is that the development of an embedding model is directed typically towards a specific purpose. So in the case of text, you might have word to vec, which is basically a word embeddings model that's able to retrieve words that have similar meaning. You might be working with another embeddings model that is more geared towards working with documents, and so on and so forth. So there are many different embeddings model for a particular input data type. So you might have a completely different embeddings model for images as well as audio. So the reason why I mention this is because I want to highlight as well that the vectors here are not random. They're carefully structured and curated such that the distance and the direction between them represents some semantic relationship. And this is how machines begin to understand the content that you're feeding it, albeit be from text, image, audio, or any other file that we discussed that actually can get converted to a vector. And this is how machines can begin to understand the content in maybe a little bit more of a human-like way. And this is done by capturing and using the complex patterns in that data to generate these things called vectors. So let's go over how these embedding models can actually be leveraged in a large language model that you might know called ChatGPT, which leverages this transformer architecture. And I just want to note that here, while we're going to give you just a brief overall overview example of how each individual step is working, it can take a postgraduate course all on its own to fully understand the intricacies that are found within each particular step. So that's just something to know. And over here, we're not going to be mentioning or talking about attention mechanisms. This is just a high-level overview, as I mentioned. So when you have a prompt, so this prompt can be, for example, what is the weather like today? What happens here is that each word in this prompt is actually converted into a unique vector. And this vector basically contains these numerical values that we just talked about that the input embedding model here has learned to associate with the semantic and the syntactic properties of each word during its pre-training phase. And then it goes on to this positional encoding layer here. So here you'll have some vector, which has some numbers, and it goes to n dimensions, which will be going in depth a little bit in a few minutes. Then what these positional encoding does is it adds a little bit more information that basically incorporates the order of the words. So this helps the model understand that weather here has come after the and before like. And basically, the reason why this is because the order of the words have a very big, profound impact on the actual meaning of the sentence. So if you think, for example, man bites dog, it's not equivalent and it's not similar in terms of its meaning as dog bites man, right? It has very different context and very different innuendos. So this whole positional encoding basically adds on to this vector and basically assigns these words within each vector the position of which that word has been found in that sequence. Then it goes on to the encoder, and basically the encoder just tries to understand the context fully from the sequence, from the vector, as well as the positional encodings, and it tries to understand the entire prompt. So it looks at, for example, how words interact with each other and understands the prompt. In this case, is basically asking about the state of the atmosphere at this particular time. So this is very important from that respect. So then you have this decoder's role here that you see, and basically it starts by getting the context established from the encoder, and then the decoder begins crafting a response, and it initiates an output embedding that starts with a starting token. You'll have some starting token here, and then based on the context, in this case, what is the weather like today, it begins predicting the next word. So let's say the first word it predicts is the word the. This word is then converted into an output embedding. That output embedding gets fed into the linear layer, and the linear layer basically assigns or ranks the probability of, or not the probability, but assigns some rank to what possible next words there are. So it could be, the next word could be weather, and so on and so forth, and it assigns some rank to that. Those ranks get fed into the Softmax layer here, and then the Softmax creates some distribution of all the ranked words and then picks a word that is probably going to be found next. So the Softmax probability distribution, in essence, is applied to the scores to turn them into a probability of how likely they are found or likely to be used in the next word. So this whole process is an iterative process because with each new prediction, it is basically based on the updated sequence of output embeddings that you see here and the context from the encoder that you have over here. So the reason why we went through this entire process is to essentially highlight the point that embeddings can be used for different purposes. Here, when we talked about input embeddings, the input embeddings here converted each word for the input text into a vector that captures its meaning as well as the linguistic role it has. And these vectors are then processed by the encoder, as we talked, to understand the nuances of the input sequence. And when we're talking about output embeddings, the vector representations of the word generated, such as, for example, the, are generated by the decoder during the language model's prediction process, and they evolve as the model constructs a response within each word embedding, influencing subsequent predictions, as we were showing from the linear layer and the softmax layer. So this was just a way to highlight that both input and output embeddings in this case may be leveraging the exact same embedding model that is maybe mapping those words into a high dimensional space that is learned from the training data. However, their purposes differ entirely because the input embeddings are all about understanding the given text, while the output embeddings are all about creating new text. And despite these different roles, they work in tandem within this model to enable a sort of some understanding as well as generative tasks, and although they may be leveraging the exact same embedding. So I think it's a good time now to talk a little bit about what dimensions are. And the first time we introduced dimensions is when we had this input sequence in the form of a prompt that gets ingested into our input embeddings. That input embedding generates some vector, and these vectors are essentially numbers that go on to n dimensions long. So what are these dimensions? So here you see that we have an array of numbers, right? These are vectors that are associated with some familiar words such as dog, puppy, cat, and so on and so forth. And the dimensions here are D1 all the way through D7, and they can be thought of as different attributes that the model has learned to differentiate and understand words. So you might be asking, when we say attributes, are these dimensions or attributes humanly interpretable? And that's not quite the case. So for example, do you mean that when we say D1, is it in a humanly interpretable dimension such as size, for example? Is it referring to size? And that's not quite the case. They are instead the result of the model's training, which adjusts these values that you have in these dimensions such that words that are used in similar contexts have similar vectors. So what do I mean by that? So let's take a closer look on, let me just change the color here. Let's take a closer look on dog, right, and puppy. And let's examine the vectors and the numbers that are associated within each dimension. And as you're seeing here, the numbers are very, very similar, right? And this is because in the training, when the model was trained, the model has learned from a vast amount of text data that dog and puppy are often appearing in similar contexts and hence should be represented similarly in this embedding space. And then in contrast to this, if you take, for example, dog and compare it to cat, you'll see that now the numbers are not very, very similar now. For example, in the second dimension, it's very, very different because this value is 0.9 and the cat value in the second dimension is minus 0.1. And this illustrates that while cat and dog are also animals, they show differences by these dimensions, and it reflects its distinctiveness from dog and puppy when we're talking about cat. And houses, for example, are entirely unrelated concept and has a very different embedding, as you see, right, from all the other ones that we can compare to the houses embedding. So in practice, these embeddings are much higher in dimensions, in the number of dimensions, and they're often in hundreds, if not thousands of them. And this allows, and the more dimensions you add, the more you might capture in terms of semantic meaning, but the trade-off here might be in the form of computational efficiency, because there would have to be a lot more processing power to generate those dimensions for each particular vector. And we're going to be talking about in just a second what happens when you are trying to retrieve, for example, you're trying to use some embedding model to retrieve some data, why it's not feasible to compare that particular query, the query's vector, to every single vector within that particular data set. So this might be an abstract concept right now, but as we go on, I feel like you'll have a better understanding of what we're talking about. So the principle remains the same, right? So words that are closer in meaning are closer in a vector space, and this enables the model to understand and generate language with a high level of sophistication. So if you're using an embedding model like ADA002, and we talked about this idea of the dimensions in reality and in practice are hundreds, if not thousands of them. If you're using ADA002, you'll see that the number of dimensions that are the output dimensions are set at 1,536. This is not something you can change for this particular embedding model. In contrast, for example, if you're using another embedding model, so let me just erase this, like word2vec, you can actually set the parameter of how many dimensions you want to have created when you are using it on your data. And this is important because you have to weigh the difference or the contrast and the trade-off between how many dimensions do I want to have, as opposed to how many dimensions are the most optimal to retrieve the accuracy that I want without over compensating in terms of computational resources. So those are the trade-offs that you would often have. So word2vec, I think typically 200 to 300 dimensions are what is recommended. If you do thousands, it just becomes inefficient. And there's a point where point of diminishing returns where no extra added dimension actually yields any benefit in terms of accuracy. And this is why 2 to 300 is generally recommended. So the reason why I say this is you need to first understand, are the output dimensions set for the embedding model that you're using? If not, what is the recommended number of dimensions based off of other people's experience? And if there's any literature that supports that. And this is important. So here, and also now I want to talk about this idea of dimensionality reduction. So this is what we're seeing in this image here. So we're taking these dimensions that are in essence, let me just put it over here, 7D, and reducing it into a two-dimensional space. And then once we reduce that into a two-dimensional space, you'll see that it's still retaining the significance of the differences between the dimensions, in that puppy and dog are very similar still, while cat is very close and house is very, very different completely. So the whole idea of dimensionality reduction is to transform high dimensional data that you're seeing into a lower dimensional space and retaining much of the significant information. So here you're seeing that 7D vectors are projected into this 2D plane. And this is possible because of dimensionality reduction. So there's techniques like PCA, TSNE, or autoencoders that are basically doing or performing this dimensional reduction behind the scenes. And this is what's making it or allowing it to have some capability of working with such a vast amount of dimensions, which would yield higher computational resources to work in a less computationally intensive environment. And I think with this, let's head on over to our Python environment and see how we can actually visualize and have a better understanding of what these dimensions are. So let's see how we can actually visualize what embeddings look like on different dimensional spaces. So here, what we have is a data table that I've created that basically looks at different types of fruits and vegetables and basically assigns some dimension to capture some specific aspect of that food, such as maybe the redness, crunchiness, and sweetness, and vitamin C content. So this is the table that we're going to be working with. It's a very small table. And what I want you to think of is those particular attributes being sort of analogous to dimensions. And even though in what we just mentioned, which is that these attributes are not actually humanly interpretable, i.e., let's say you create some embeddings for some data, you can't pull out these dimensions in these human interpretable way to say, for example, redness, crunchiness. This is just a way for you to sort of conceptualize what we are referring to dimensions as it is depicting some sort of meaning of those words. But in this case, we're using it as an abstract way to visualize or think about what dimensions actually are. So if we are to plot, for example, on a two-dimensional space, all these different attributes, but only looking at sweetness and vitamin C content, we're going to be looking at a two-dimensional graph. And this is what we're looking at here. So this is a 2D visualization. And what I want you to take away from this visualization is that we're only capturing two dimensions here. And by just quickly seeing, you'll see that maybe things like orange and apple might be very similar in terms of this dimensional space because they are very close. They are the closest together as opposed to orange to carrot, right? So what happens when you begin adding more dimensions? And these dimensions are features or attributes. And let's now look at how we can visualize all these different attributes or dimensions into maybe a 3D plot. So let's visualize these four dimensions into 3D, and I have this already written here. And this is what you would probably get. Just one note, however, is that while we're only seeing 3D, if in reality, like I said, you'll have maybe hundreds, if not thousands of dimensions. And for you to visualize what that is, then it would take an extreme amount of computational resources. And it just doesn't become efficient at that point. But this is just a way for you to sort of conceptualize this idea of adding what happens when you add more dimensions and what is this dimensional space that we keep referring to and why is this important. So if you see in our previous graph here, you'll see that orange and apple are the closest in terms of their semantic similarity as it relates to vitamin C content and sweetness. But what happens when we begin adding more dimensions like crunchiness or redness? And you'll see that now they are not the closest together, at least visually. And we're going to talk in a second about how we can calculate this distance between these two vectors. And as we said, vectors are basically just an array of numbers depicting the values for those dimensions. So here you see that before, when we're visualizing apples and all these different fruits and vegetables into a 2D space, apple and orange were the closest together, but now you see them further apart. And this highlights or this illustrates the point that as more dimensions are added, things may be closer together, be brought closer together in this dimensional space, or things might be further apart. And this is what I really want you to take away from this. And like I said, in reality, in practice, these things are not humanly interpretable. This is just a way for us to sort of abstract away this idea of dimensions and think about them from a way we can understand. So how do we measure the distance? So this is the high dimensional space where all these different food items are placed. How can you measure what's the distance between apple and orange? How can you assign a value towards that similarity or towards that distance? And this is where we can use something called the cosine similarity. And there's other methods of calculating this distance, but I will mainly be going over what cosine similarity is. So here we have the numerator, and by the way, this formula is the exact same as this formula. So if we take the numerator here, this is just calculating the dot product of the first vector and the second vector. So let's say you have vector A and B. You'll take the first dimension of vector A and multiply by the first dimension of vector B. You would add that to the multiplication of the second dimension of vector A with the second dimension of vector B, and so on and so forth, until you reach n number of dimensions that you have in your vector. So that's how you would calculate the numerator. It's basically the sum of the products of the corresponding elements from each vector. So this value that we get, right? This sum gives you a single number, and this basically represents how much one vector extends in the direction of the other. And the dot product, essentially, this part, is maximized when when two vectors are basically pointing in the same direction. Basically, it's 0 when they are perpendicular to one another, and is minimized basically when they point in opposite directions. So in the context of what we talked about in embeddings, and within the context of embeddings, so higher dot products, so higher values of this would basically mean that the product indicates more similarity between the vectors. And this suggests that maybe the words or documents that are being represented have more semantically similar meanings. So that's for the first part. Let's look at the second part here, which is the denominator. And so let's just erase all this. So the denominator of this particular formula, let's examine that in closer detail. So here we have essentially the product of the magnitudes of vectors A and B that have actually been normalized. So the denominator actually normalizes the dot product by the vector's magnitude. So the breakdown of this would be, so let's say you have some vector, this is vector A, you have some amount of dimensions, extends to an. So basically what the bottom of this would look like is that you would have the square root of a1 squared, which is the first dimension, plus a2 squared, and so on until a. This also goes for the second, and this also goes for the second vector as well, which is vector b. So then the denominator is a product of the magnitudes of those vectors. So then it would be this, and then you would multiply that by the exact same thing, which would be for vector b. So it would be 1 squared, b2 squared, all the way till an. Then that's how you would get the denominator. So what this does is basically scales the dot product, which is the top, in a range of -1 to 1. So the normalization basically allows the cosine similarity to measure only the directionality of the vectors and not things like their length. And it makes it a measure of orientation similarity and not magnitude. And this is the difference between the Euclidean distance as well as the cosine similarity. So by dividing essentially, if we just clear this, so by taking the top, which is the dot product, and then basically the magnitude of those vectors, you're essentially finding the cosine similarity effectively measures the cosine of the angle between those vectors, which is basically normalized and scale invariant metric of their similarity in orientation in space. So when you find this angle, you'll see it gives you a value between -1 to 1. And cosine similarity of 1 will essentially mean that the vectors are pointing in the same direction, and this means very similar. And then the opposite side of this is also true, and when it's -1, it means that they're pointing in completely opposite directions, and this means that they're not similar at all. So with this said, let's see how we can calculate it in Python for two particular vectors. So if we were to calculate the cosine similarity between apple and orange, what we would do is what we just described above. First, we have to get the dot product of those two vectors. And this is what we're doing here. We're assigning it to apple vector and orange vector. And this is essentially grabbing all the dimensional values of apple as well as orange and puts it into an array. And then from there, we take the dot product of vector A and vector B. And vector A and vector B essentially are the apple and the orange vectors. We normalize the apple vector as well as the orange vector, and then we take the numerator and then we multiply the two normalized vectors together, and then we calculate the cosine similarity and we return the value. So the value here is 0.76, indicating that it's pointing and directing, the direction is the same and they are very similar to each other. And this is how you would calculate it behind the scenes. And why is all this important? So up until this point, we talked and dove deep into embeddings, how embedding models can be used within large language models like ChatGPT, and we referenced the transformer architecture for that, where you had two different embedding models doing two different things. We then dove into dimensions and how you can visualize them, as well as how you can think about dimensions. We then moved forward to how you can calculate the differences or the similarities between two vectors using the cosine similarity. And now you might be wondering how you can leverage embeddings within your application. So in the previous video, we talked about how you can leverage your own data with some LLM of your choice without having to fine-tune that LLM. And this was done through a framework that we called RAG, and it's basically stands for Retrieval Augmented Generation. And the flow of how that would work is you would have some data sources, and those data sources would get indexed into Azure Cognitive Search at that time, but now it's called Azure AI Search. And when there's a query that's incoming in, it will basically also get indexed and match the index of the query to the index of your data sources and pull the relevant information that way using some keyword-based matchmaking. And this is efficient and this is useful when you are mainly concerned with matches of keywords, but obviously struggles with understanding the semantic meaning of the query. And this is why embeddings were introduced into Azure AI Search, because it wants to move away from being just simple keyword matchmaking to basically a more nuanced and semantic understanding of the queries. And this is what embeddings solve, and basically from everything that we talked about earlier. So in essence, what it would do is the flow would then be, you would have some query, and this query would then be vectorized using some embedding model, right? And if you're using Azure OpenAI, then you would probably be leveraging the embedding model OpenAI. It's called ADA 002. But you can very well leverage BERT, another popular embeddings model, or you can leverage Word2Vec. It really doesn't matter. But the whole idea is what your data sources are being vectorized in an embedding model that is suitable to a particular use case that you are looking to do, right? So after that occurs, it would then need to be stored somewhere. So Azure AI Search can be that place where you store these vectors that have been created from the embeddings model. You don't have to use Azure AI Search. You can use Chroma, DB. You can use FICE. You can use Cosmos. And the reason why is because these databases have vector optimizations for retrieval, as well as working with vectors in general. So you might want to consider, if you don't want to use Azure AI Search, you can use any of those alternatives because they're optimized for vectors. Then, because we have all this now, is we have some query that's incoming in. Now the query gets embedded through the same way you embedded maybe the data sources based off of your use case. And then it would try to match the vectors to the closest vector. It would try to match the query vector to the closest vector in your vector database. And how it does this is through this algorithm called Approximate Nearest Neighbor. And basically, Approximate Nearest Neighbor comes from the family of algorithms that are called HNSW, which stands for Hierarchical, Navigable, Small World. And in essence, what this is, and we're going to just showcase a little bit on a very high level what that looks like. But in essence, what I want you to think about is ANN, also what Approximate Nearest Neighbor is. It just stands for ANN. It's just an algorithmic approach to basically efficiently find the closest points to a given query point in a high dimensional space, but you are trading off a little bit of preciseness, or because it's not exact matches, with speed, because it's very, very fast. So how does it do all that? And why don't we examine on a high level what that looks like? So before I dive deep into Approximate Nearest Neighbors and how it works, I want to talk about this concept of integrated vectorization. Integrated vectorization. So right now, when you are using the Azure AI Search, the service itself doesn't actually have built-in capabilities to convert your data into vector representations. And this means that when you have some application code that is writing the embeddings to transfer your data to embeddings, it doesn't have, you basically have to make an external call to Azure OpenAI because you want to leverage ADA 002, which we said is the embeddings model for semantic understanding. And for you to transform your data into those vectors, you have to make it this external call to Azure OpenAI. But right now we have this idea of integrated vectorization, which in essence is a preview feature. This is a preview feature. And what it is basically has built-in vectorization process that's integrated within Azure AI Search. So you don't have to externally make the call to ADA 002 in Azure OpenAI. And this is very important because some corporations or some use cases require very strict policies as it relates to ingress and egress of data and calls or API calls. And this, in essence, will solve it. This feature is in preview currently. So that is just something to know that I just wanted to highlight here. So how do Approximate Nearest Neighbors work? And as we said, that Approximate Nearest Neighbors are used from or derived from these family of algorithms called HNSW. What these algorithms do is they create these multi-layered graph representations where each layer that you're seeing here, as well as here, are representing some subset of your data. The top layer that you're seeing, this could be the top layer, basically consists maybe just a few vectors, and these vectors are classified as nodes here. And as you keep going down each layer, there are more and more nodes. And we'll get into a second why this is important, but just a few things that you should note. Within each layer, there could be connections between nodes, and these connections are called edges. And within how an edge is established is through some distance threshold between these two vectors. So if you remember that we talked about this cosine similarity distance measurement that you can use to assign the semantic similarity between two vectors. So in essence, if you're using this, then you can say that if the distance between these two vectors are above a certain threshold, then create this edge and connection between these two vectors. You can have connections between vectors within the same layer, as well as you can have them across layers. So one vector can have multiple connections and so on and so forth for all the other ones as well, right? Here, and so on and so forth. The maximum number of connections a node can have is denoted by this variable called m, just called average degree. And this is important because we're going to get to in a second how the algorithm knows what nodes to assign to which layer that you're seeing in this graph. And I think this is a good time to go into the math just briefly on what that looks like. So how the algorithm knows what layer or level the node will fall in is denoted by this formula, which says that if you take the negative natural logarithm of a uniformly distributed variable between 0 and 1 and multiply it by some scaling factor, you will then be able to assign the level to that particular vector accordingly. So what it's doing is it's taking a value between 0 and 1 that's randomly generated, and when you take the natural logarithm of that, you're going to get some negative value. This is multiplied by another negative value to basically give us positive 1, and then this is going to be used as a scaling factor to essentially create the probability that the nodes that are going to be generated are less likely to appear at the top as opposed to the bottom. So if we look into just a little bit of the math of what's happening here is when you take the negative natural logarithm of the uniform variable here, let me change the color. You are essentially converting this into an exponentially distributed variable. And this is just basically due to the properties of logarithmic functions when you apply, when are being applied to uniform distributions. The factor of m here are essentially scaling that exponential distributive values, and this basically controls the spread and the decay rate of the distribution. And this directly impacts how nodes are distributed across different levels in the graph. So this is actually denoted as 1 over ln times the number of average degrees, as we mentioned. So in the case that it's 10, for example, let's say m is 10, the value of little m, or the scaling factor, is going to be around 0.434. So in essence, if we have, let's say we have the number of levels is 3, we have the maximum or the average degree to be 10. We can then plug in the number of nodes, and let's say the number of nodes are 20 that we have in our graph, and this is how many vectors, i.e. vectors. If we do one step or one cycle of this formula is going to be around, so let's say we have negative ln, and the value is 0.9 that gets randomly generated, and you multiply that by 0.434, then you will have the level assigned to 0 because you're taking the float of this equation. And as a result, you'll get 0. So that first node will get assigned 0, and so on and so forth for all the rest of the 20 nodes that you have here. So if we were to go back into our graph here, let's see what is actually happening behind the scenes when you are creating a query or when you're trying to retrieve some data. So when you're trying to retrieve some data, you have it'll get randomly assigned to the top layer in this top layer space here. And then it will measure all of the different distances between all the different vectors that it has here. And this is basically using maybe cosine similarity or any other distance metric. The closest vector, so let's assume that this is the closest vector to x, it will use the search path of x to go to the bottom layer. So what that means is x, this query, so x here is a query, and it figures out that this particular node is the closest to it in terms of maybe cosine similarity, it will go to this node and it will follow the path based off of the edges that it has to all the other nodes in the second layer. And then it zooms and then does the same thing. It says maybe it finds that this is the closest cosine similar, or this is the closest vector based off of some distance metric that you specified. It will then follow this path. It will have a very more localized search because there are the most there's the most nodes in the bottom layer. And then from there, it's able to retrieve one particular or a subset of vectors, and then those vectors are returned then to the algorithm, to the user, to basically showcase that these are the closest things related from your documents. So what you're seeing here is there's a little bit of a trade-off, and the trade-off becomes in the form of accuracy and speed. The reason why it's maybe a little bit less accurate is because you're not measuring the distance between the query and all of your data set. You're measuring it for a subset. Basically, you're assigning it to a random place within the top layer, and then it's measuring the distances between the vectors that are closer to it, which in essence means that there may be other vectors that are not being included in this particular measurement that might have more context or might have more similarity. So I think I just wanted to highlight on just a high level what it is, or how this algorithm is working, and some math that's going behind it, just for your knowledge to understand when you're maybe choosing different parameters for this algorithm. It's important to understand these different metrics or these different concepts, because it will help you immensely to get the best value or the best response from your application. So here you'll see we are in the Azure AI Studio for the Azure OpenAI service. We went through all of this in greater detail in previous videos in our Azure OpenAI 101 series, but just a few additions that maybe we can highlight here is there's these things called content filters, and by default there are things that you or the model will, or like ChatGPT, will automatically detect and flag. And this is if when the content is somehow harmful, or there's some hate speech, or there's some self-harm. And these are all different thresholds that now you can adjust, and you can create a configuration for that particular threshold. If you want to completely remove it, even if the threshold is low, if you want to completely remove it, you have to create a ticket, and you have to basically communicate what the purpose and the intention for removing these filters are. And then based off of that criteria, these can be completely removed for you as well. So also another thing is DALL-E is also in preview, but I think it's only for a few select regions. So you can also glance and work or just experiment with DALL-E here. So but what we really want to discuss here is just the chat feature, and we discussed it in our previous video when we were talking about RAG applications and how to use your data with ChatGPT. So now when we add a data source, and I've already added some research paper documents into Azure AI Search and has already been indexed. So if I select that particular service, and as I said, Azure AI Search was formerly known as Azure Cognitive Search. And if I select the index here, you see that now we have an option called Add Vector Search to this resource. So when you select this and you select an embeddings model that we have created, and I'll show you this in just a second, basically what we're doing is the index, or the data within our index within Azure AI Search, is going to be vectorized and stored within Azure AI Search. So when we are chatting with GPT-4 in this case, because this is our deployment, it will be retrieving the documents that are appropriate using vectors, and using the vector database of which it gets stored all the vectors that have been embedded from your documents. So you acknowledge that there's some there will be some usage costs here. So we just click next. This is for citations, making your citations look pretty when you are, or when the model responds back with your knowledge or with your documents. And we click next, and here you'll see that you have different search types. So just simply vectors is basically when you want to find documents that are semantically similar to a query, even if there are no keywords, even if there are no keyword matches in Azure AI Search. So this is basically more useful for longer queries, and or descriptive queries or questions. And then you have vector plus keyword, and this is basically if you want to combine the strength of both vectors as well as keywords, then this is something that you can think about. And then you have hybrid plus semantic. And this is pretty straightforward from there. So what we would generally recommend is play around with the different search types based off of your use cases. But typically, you would want to start with hybrid plus semantic, and then work your way down to see what's giving you the best accuracy. So here, let's just select hybrid plus semantic. We don't have any search configurations here. Let's acknowledge, and then click next, and then save and close. And it was this quickly to be able to, one, embed the documents. Number two, now you can start chatting with those documents and asking questions about them We also have this idea of importing your setups. Let's say you create some parameters and you have found the optimal configurations. We also talked about this in our previous videos and how you can work around with them. You can export the setup and then import them, because this is a stateless session, meaning when you get off or when you exit this window, this is not saved. So you have to also think about that. If you are thinking about building an application where it is leveraging things like embeddings, I'm going to leave a GitHub repo in the description below that you can reference, and that's going to serve as a foundation of how you can work with all this data, as well as build your own ChatGPT or your own LLM application. So with that being said, I think we covered a lot of ground here. We talked about embeddings, dimensions. We went into the math behind how it's working behind the back in the back end. Talked about the transformer architecture and how you can leverage multiple embedding models for different purposes within the same architecture. We also talked a little bit about how you can measure the distance between two vectors, how the hierarchical navigable small world algorithm works within the context of approximate nearest neighbors. And now we just showcased in a very high level how you can integrate all these concepts in a very simple way using the Azure OpenAI Studio. If you enjoyed this content and if you learned something, please consider liking, subscribing, and commenting. That really helps out with the algorithm. And I'll see you in the next one.